Hello everyone, myself Priya. This is an audio recording for visually impaired students. The name of the chapter is Chemical Kinetics. Introduction. Chemical kinetics is the branch of chemistry which deals with the rates of chemical reactions, the factors which affect the reaction rates, and the mechanisms by which these reactions occur. In other words, chemical kinetics tells us how fast a particular reaction takes place and what mechanism it follows. Also, it tells us how the reaction rate is dependent on variables like temperature, pressure, and the concentration of the reacting species. The chemical reactions can be classified into following categories on the basis of their speeds. Instantaneous reaction, which occur at very fast speed. These reactions occur as soon as reactants are mixed and is particularly not possible to measure the speeds of such reactions by ordinary methods. Such reactions include several ionic reactions, neutralization reactions of acids and bases. Extremely slow reaction which proceed at very slow speed, for example rusting of iron, combination of hydrogen and oxygen at ordinary temperature. These reactions occur at such slow speed that it is not possible to determine the rate of reaction. Reactions which proceed at measurable speed. There are chemical reactions which proceed at moderate speed, which can be easily measured. Some examples of such type of reactions: hydrolysis of ether, inversion of cane sugar, and decomposition of HI. Different chemical reactions proceed at different rates. An obvious reason for this is that a chemical reaction involves breaking of bonds in the reactants and forming of new bonds in the products. The energy required for bond breaking and energy evolved for bond formation is different for different reactions. That is why different reactions proceed at different rates. The instantaneous reactions involve just combination of ions that are already present in solution. Hence, these reactions occur at very fast rate. The reactions with measurable rate are the focus of attention in chemical kinetics. Chemical kinetics is concerned with the following aspects: the rate of reaction and the rate laws. What is the effect of temperature, pressure, concentration, and catalyst on the rate of reaction? What is the mechanism of the sequence of steps by which the reaction occurs? Rate of a chemical reaction. The rate of a chemical reaction or the reaction velocity may be defined as the change in concentration of any of the reactant or the product per unit time. For example, consider a simple reaction A to B. Thus, rate of reaction decrease in concentration of A upon time taken is equals to increase in concentration of B upon time taken. Units of rate of reaction. Rate of reaction has units of concentration divided by time. The concentration is usually expressed in moles per liter. For gaseous reactants, instead of concentration, we take pressure in atmosphere, and time may be expressed in seconds, minutes, or hours. Therefore, the units of reaction rate as follows: mole time minus 3 second inverse, mole little inverse minute inverse, mole little inverse hour inverse. For gaseous reactants or products, the concentration term is expressed in terms of partial pressure in atmosphere. Therefore, the units of rate of reaction will be atmosphere second inverse, atmosphere minute inverse, atmosphere hour inverse. The molar concentration the molar concentration of reactants and products keeps on changing with time. Therefore, the rate of reaction is not uniform throughout but keeps on varying. Therefore, it is more appropriate to express the rate of reaction at a particular instant of time. Such a reaction rate is called instantaneous rate of reaction and is defined as the change of concentration of any one of the reactants or products at a particular instant of time. Expressing the instantaneous rate of reaction. According to law of mass action, the rate of reaction depends upon the molar concentration of the reactants. As the concentration of reactants changes with time, so the rate of reaction also changes with time. Therefore, it is more appropriate to express the rate of reaction at a particular instant of time. To express the rate of reaction, a small interval of time dt is taken and it is assumed that the rate of reaction remains constant in this interval of time. If dx is a small change in concentration of any of reactant or the product, then the rate of reaction is expressed as rate of reaction is equals to dx upon dt. In case of reactants, concentrations decreases with time, therefore a negative sign is put before dx upon dt. On the other hand, the concentration of products increases with time, and hence a positive sign is written before dx upon dt minus dx upon dt, sorry, plus dx upon dt. Consider the following reaction. The rate of such reaction is expressed in terms of fall of concentration of a reactant or increase in concentration of a product. Thus, the rate of reaction based on the rate of change of concentration of each species is written as rate of reaction dx upon dt is equals to minus dA upon dt is equals to minus dB upon dt is equals to plus dl upon dt is equals to plus dm upon dt. It may be emphasized that the rate of reaction is always positive. The negative sign in above expression indicates the fall in concentration of the reactant, whereas the positive sign in this expression indicates that increase in concentration of the product with the passage of time. Hence, dA dB represent the small decrease in the concentration of reactants A and B, and dL and dm represent the small increase in the concentration of products L and M. For a general reaction, small a into capital A plus small b into capital B gives us small l into capital L plus small m into m. The rate of reaction is written as follows. Measuring the here small a, small b, small l and small m are the stoichiometric coefficients measuring the rate of reaction. The rate of a reaction can be measured by plotting a graph between the concentration of any of the reactants as a function of time. The concentration of any of the reactant or the product is measured at different intervals of time. For this, it is necessary that all other variables except concentration which may affect the reaction rate remains constant. Usually a reaction is carried out and small amount of reaction mixture is withdrawn at small intervals of time. This reaction mixture is cooled to a temperature below 0 degrees Celsius by keeping it in freezing mixture. By doing so, the reaction is arrested. No further reaction takes place. Now, the concentration of any of the reactant or product is determined by suitable method, usually titration. After determining the concentration of a reactant or a product, a concentration time curve is plotted. It is not always required to stop the reaction for measuring the concentration of any species at various time intervals. The same information can be obtained by noting the changes in observable properties like change in color, change in pH, volume, pressure, optical rotation with time. Accordingly, the graphs are plotted to calculate the rates of reactions. All these methods will be taken up as we proceed in the chapter. However, if change in concentration of a reactant or a product is measured with time, then the rate of reaction is determined as follows. Show the variation of concentration of a reactant with time and the change in concentration of a product with time. In such type of concentration time curves, the reaction rate is determined by two methods. The rate of reaction at any instant of time can be determined by drawing tangent to the concentration time curve at that particular instant. The slope of the tangent then have the required rate of reaction at that instant. A small change in concentration dx in a small time interval dt is noted directly from the concentration time curve, assuming that the rate of reaction remains constant during this small interval of time. The quantity dx upon dt gives the required rate. Show the increase in concentration of a product with time. The rate of reaction can be determined by drawing tangent to the curve of the given instant of time or by reading directly the values of dx and dt from the curve. Factors affecting the rate of reaction. The rate of a reaction is influenced by the following factors: Nature of reactants, concentration of reactants, temperature of system, pressure of a catalyst, exposure to radiation, of the solvent. For reactions in heterogeneous system in which a reactant is in solid state, the surface area of reactant also becomes an important factor which affects the rate of reaction. By studying these factors which affect the reaction rates, it becomes possible to control the rate of reaction. Nature of reactants. Substances different in activity and hence in the rate at which they react with other substances. For example, active metals displace hydrogen rapidly and vigorously from acids, while the less active metals react slowly. Hence, the rates of reactions are affected by the nature of reactants. Following examples clearly show the effect. Oxidation of nitric oxide and carbon monoxide in air. About two reactions seem identical. There are same number of moles of reactants and products in both the cases and both are oxidation reactions, but they different in their rates. The reason is that the nature of reactants NO and CO must be different, hence there is difference in the rates of these reactions. Combination of chlorine and bromine with hydrogen, both these reactions are similar as shown ahead. Cl2 plus H2 to HCl, Br2 plus H2 to HBr. Under similar conditions, the first reaction is fast while the second is slow. This difference in rates of two reactions can be attributed to the nature of halogen. So, rates of reactions are influenced by the nature of reactants. A chemical reaction involved the breaking of old bonds and formation of new bonds. The reactivity of a substance is therefore related to the ease with which the specific bonds are broken and the number of such bonds involved. As the amount of energy required to break the bonds is different in different reactants, hence the rates of reaction also vary with the nature of the reactants. Concentration of reactants. It has been observed that the rate of a chemical reaction keeps on decreasing with time. The concentration of reactants of maximum at the start of the reaction and therefore the rate of change of concentration is also maximum. As the concentration of the reactants decreases, it brings about the corresponding decrease in the rate of reaction. This clearly indicates that the rate of a reaction is directly proportional to the concentration of the reactants, the change of concentration of the reactants and therefore the rate of reaction with time. From above figure, it is clear that at the start of the reaction, the rate of reaction is large and it decreases with the passage of time. Therefore, to increase the rate of reaction, we should increase the concentration of one or all the reactants. In a gas phase reaction, the increase in pressure of the reactant gases increases the rate of reaction. With increase in pressure, the number of molecules per unit volume increases and therefore the rate of reaction increases. The effect of concentration of reactants on the reaction rate may be explained in terms of collision theory. According to collision theory, the rate of reaction depends upon the number of collisions per second between the reactant molecules. By increasing the concentration of one or all the reactants, the number of collisions increase and it leads to an increase in the rate of reaction. Temperature of the system. In general, an increase in temperature increases the rate of almost all chemical reactions. Besides increasing the rate of reaction, in many cases it is observed that temperature even indicates the reaction. For example, hydrogen and oxygen do not react at room temperature but react radially to form water when electric spark is passed through them. The rate of all chemical reactions increases with increase in temperature. A general approximate rule is that the rate of most of the chemical reactions becomes double or even triple for every 10 degrees Celsius rise in the temperature. This is also called temperature coefficient, which is defined as the ratio of the rate constants of a reaction at two temperatures differing by 10 degrees Celsius. Thus, temperature coefficient is equals to rate constant upon rate constant. Rate constant T plus 10 degree Celsius rise में where K1 and KT plus 10 are the specific rate constants at T degree Celsius and T1 T plus 10 degree Celsius respectively. For example, the temperature coefficient K398 by K298 for the saponification reaction of ethyl acetate with sodium hydroxide is 1.75. whereas the value of temperature coefficient for reaction between methyl iodide and sodium methoxide in solution is approximately 2.9. The marked coefficient of temperature on the reaction rates can be explained in terms of number of collisions between the reacting molecules. The increase in temperature will increase in the number of collisions and thus the rate of reaction increases. But an increase in temperature by 10 degrees Celsius increases the number of collisions by about 2%. That this fact is unable to explain the 2 to 3 fold increase in reaction rate for every 10 degree Celsius rise in temperature. Explanation of effect of temperature on rate of reaction. The increase in reaction rate with increase in temperature is explained on the basis of collision theory. According to collision theory, the chemical reaction occurs as a result of collisions between the reacting molecules. However, all collisions do not result in chemical reaction. Only effective collisions between the reactant molecules result in formation of products. According to collision theory, only a small fraction of collisions is effective in bringing about the chemical reaction and the rest of the collisions are ineffective. For an effective collision, the collision molecules must have more than or equal to certain minimum amount of energy called threshold energy. Thus, threshold energy may be defined as the minimum energy which must be possessed by the colliding molecules to cause a chemical reaction on collision between them. If the energy of the reacting molecules is less than this value, collisions will be ineffective. All the molecules in a substance do not possess the same energy. Thus, there is a distribution of energies among the reacting molecules. If the energies of molecules are plotted against the corresponding fraction of molecules at a particular temperature, a curve of the type this is called Maxwell's distribution of energies. Okay, it corresponds to the minimum or the threshold energy required for causing effective collisions. The molecules having energy equal to or greater than E will result in formation of products. To explain the effect of increase in temperature on the number of effective collisions, consider the energy distribution of molecules at two different temperatures T1 and T2, where T2 is equals to T1 plus 10 degree. It is evident from the figure 3 that when the temperature is increased from T1 to T2, the curve gets shifted towards right, indicating that the number of molecules with higher energies has increased. The shaded area ABEF at temperature T2 is almost twice as large as shaded area ABCD at temperature T1. Therefore, the fraction of molecules possessing activation energy has increased approximately 2 times for a rise of 10 degrees in temperature. Since the rate of reaction depends upon the number of molecules which possess energies larger than activation energy, therefore we may conclude that the rate of the reaction becomes almost double for every 10-degree rise of temperature. Concept of activation energy barrier. Familiar reactions such as burning of coal in air, combination of hydrogen and oxygen gases do not occur unless some extra energy in one form or the other is supplied to them. This is because in such reactions the reactant molecules do not possess energy equal to or greater than threshold energy under normal conditions. So there is no reaction, thus some extra energy has to be supplied to the reactants to bring their energy equal to the threshold energy, and then the reaction starts. The excess energy which must be supplied to the reactants so that their energy becomes equal to threshold energy is called activation energy EA. It is equal to the difference between the threshold energy for the reaction and the energy possessed by all the reacting molecules. That is, activation energy is equal to threshold energy minus energy possessed by the reacting molecules. EA is equals to ET minus ER. This is shown graphically in figure 4 that for a reaction to occur, the colliding molecules have to absorb some energy and cross the activation energy barrier. The activated complex has a very short lifespan and splits into products. Activation energy plays an important role in completing the rates of reactions as already discussed. The oxidation of NO is a fast reaction, whereas that of CO is a slow reaction. In case of oxidation of NO, The activation energy is small, thus only a small increase in energy enables reacting species to cross the energy barrier to form NO2. Therefore, the reaction is fast at room temperature. However, in case of oxidation of CO, the activation energy is high, so large amount of energy is required by reactants to cross the activation barrier. Hence, the reaction is slowed at room temperature. Thus, we conclude that if the activation energy is low, the reaction is fast, and if the activation energy is high, the reaction will be slow. Presence of a catalyst. A catalyst is a substance which increases the rate of a chemical reaction and can be recovered chemically unchanged at the end of the reaction. For example, manganese dioxide speeds up the thermal decomposition of potassium chlorate. Manganese dioxide acts as a catalyst in this reaction and can be recovered unchanged at the end of the reaction. The catalyst provides an entirely new path for the reaction in which the reactants are converted to products quickly. As shown in figure 5, the catalyst forms a new activated complex of lower activation energy. This means that the activation energy becomes lower for the catalyzed reaction than that for uncatalyzed reaction. Consequently, the larger number of molecules can cross the lower activation energy barrier, and hence the rate of reaction also increases. In figure 5, the solid line shows the path for uncatalyzed reaction and dotted line shows the path for uncatalyzed reaction. Following points must be noted about the function of catalyst. The catalyst does not change del E of the reaction. This is clear from the figure 5 that the addition of the catalyst does not change the energy of the reactants and the products EP, so that del E remains the same. Although the catalyst speeds up the reaction, but it does not affect the position of equilibrium in case of reversible reactions. This is because the activation energy for the forward reaction and backward reaction is reduced to the some extent. As a result, the increase in the rate of reaction forward and backward reactions is same, and hence the positions of equilibrium remains unaffected. However, catalysts increase both the rates, hence the equilibrium is attained earlier. Exposure to radiation. In some cases, the rate of reaction is considerably increases by the use of certain radiations. The photons of these radiations possess sufficient energies E is equals to h mu to break certain bonds in reactants. For example, reaction of hydrogen and chlorine takes place very slowly in the absence of light. However, in the presence of light, the reaction takes place very rapidly. Nature of the solvent. Nature of the solvent also affects the rate of reaction. These effects can be studied under following properties of solvent: magnitude of dielectric constant of the solvent, polarity of the solvent, effect of solvation. Magnitude of dielectric constant of the solvent in case of ionic reactions in solution, the inter-ionic forces are largely affected by the dielectric constant of the solvent. Therefore, the rate of reaction is found to vary with the dielectric constant of solvent according to the following equation, where D is the dielectric constant of the solvent and A and B are the constants of two ions in solution. According to above equation, the logarithm of the rate constant should vary linearly with reciprocal of dielectric constant of the solvent at a particular temperature. Therefore, a plot of logarithm K with 1 by D should give a straight line. Polarity of the solvent. For reactions between polar reactants and rate of reaction is greatly affected by the polarity of the solvent. It has been observed that a polar solvent increases the rate of reaction in which the product formed is more polar than reactants and decreases the reaction rate if a product formed is less polar than the reactants. For example, formation of quaternary ammonium salt formed by reaction between triethylamine and ethyl iodide is favored by increasing polarity of solvent as shown in table 1. This is because this product is more polar than either of the reactants. On the other hand, the reaction between acetic anhydride and ethyl alcohol giving rise to ethyl acetate is not favored by increasing polarity of the solvent. The reason being the product formed here is less polar than the reactants. So the solvents which favor the formation of quaternary ammonium salts trend to slow down the esterification reactions in which the products are of lesser polarity than the reactants. The order of polarity of solvents in table 1 is nitrobenzene is greater than benzene is greater than hexane. If the reactants and the products do not differ much in polarity, then the effect of polarity of solvent is insignificant on the rate of reaction. For example, in decomposition of nitrogen peroxide to form nitrogen trioxide and oxygen, the reaction rate is almost unaffected by the polarity of the solvent because the reactants and products are the almost same polarity. This fact is clear from the data given in table 2. Influence of solvation. The rate of reaction is largely affected by the degree of solvation of the reactants and the activated complex. The solvation of reactants or activated complexes lowers their potential energy by an amount equal to solvation energy. Three different cases of solvation energies. Case 1. The reactants are appreciably solved, but the activated complex is not. In this situation, the potential energy of reactants is lowered due to solvation. As a result, the energy of activation for the reaction increases and the rate of reaction decreases. Case 2. The activated complex is solvated, but the reactants are not. In this case, the potential energy of activated complex decreases due to solvation. The energy of activation of the reaction decreases, consequently the rate of reaction increases. Case 3, both the reactants and the activated complex are solvated. In such a situation, the potential energy of reactants and activated complexes decreases due to solvation. The net result is increase in the activation energy of reaction, and hence the reaction will take place slowly than in a solvent in which the reactants and activated complex are not solvated. Concentration dependence of reaction rates. Law of mass action. When a chemical reaction proceeds, the reactants get converted into products. As a result of the concentration of reactants decreases while that of products increases. The quantitative relationship between the rate of reaction and molar concentration of the reacting substance is known as law of mass action. According to this law, at a given temperature, the rate of a chemical reaction is directly proportional to the product of the molar concentration of the reactants. Consider a simple reaction: small a into capital A plus small b into capital B gives us products. According to law of mass action, the rate of the reaction may be expressed as rate is equal to K into A to the power A B to the power B, where capital A and capital B are the molar concentrations of reactants. K is a constant of proportionality and it is called rate constant or velocity constant. Now, if concentration of each of the reactant is unity, then rate of reaction is equals to rate constant. Thus, the rate constant of a reaction at a given temperature may be defined as the rate of a reaction when the concentration of each of the reactants is unity. Hence, the rate constant is also called specific reaction. Rate law expression. The actual dependence of rate on concentration of reactants or products is measured experimentally. For example, in the reaction A into A plus B into B gives us products. The rate is K A into B, A to the power A and B to the power B, where P and Q are experimentally determined powers of concentration of reactants A and B respectively, on which the reaction rate depends. The power P and Q may or may not be equal to the coefficients A and B in the reaction. The expression is a rate law or rate equation. Rate law differs from the law of mass action. The rate law gives experimentally observed dependence of rate on the concentration of reactants. The powers of concentrations of reactants in rate law expression may or may not be the same as the coefficients of concentrations in the balanced chemical equation. The rate law expression is rate is equals to K A to the power A into B to the power B. Order of a reaction. Order of a reaction is defined as the sum of the powers to which the concentration terms are raised in the rate law expression to express the observed rate of the reaction. Thus, if the rate of a reaction A into A plus B into B gives us products is given by rate law as rate is equals to minus dx upon dt gives us K A into P and B to the power Q. Then the order of reaction n is equals to P plus Q. If n is equals to 1, the reaction is said to be first order reaction. If n is equals to 2, the reaction is said to be second order, and so on. Reactions of first order Decomposition of N2O5. N2O5 gives us 2NO2 plus half 2O2. Decomposition of ammonium nitrate in aqueous solution. Reactions of second order. Decomposition of NO2. Reactions of third order. Reactions between NO and Cl2. Reaction between NO and O2. Reaction of fractional order. Decomposition of acetaldehyde. And reaction between H2 and Br2 gives us 2HBr. Zero order reactions. A number of reactions are known in which the rate of reaction is independent of the concentration of the reactants. For example, the decomposition of ammonia at the surface of metals like platinum. The rate of reaction is independent of the concentration of ammonia. Thus, a reaction is said to be zero order if its rate is independent of the concentration of the reactants. In such reactions, the rate of reactant remains constant throughout. The amount of the substance reacted is proportional to the time. Zero order reactions are relatively uncommon. Many photochemical reactions and heterogeneous reactions have been found to be in zero order. Photochemical reactions. The reactions which take place in the presence of light are called photochemical reactions. Many photochemical reactions, formation of HCl form H2 and Cl2, are examples of zero order reactions. The kinetics of the combination reaction of H2 and Cl2 is the presence of light can be studied in the laboratory by a simple experiment. A test tube filled with a mixture of H2 and Cl2 gas is inverted in a trough containing water. A setup is exposed to sunlight and the photochemical reaction takes place. The HCl formed is soluble in water. As a result, the level of the water rises in the test tube. It is found that after some time the amounts of H2 and Cl2 decreases but their concentrations remains unchanged. This proves that photochemical reactions between H2 and Cl2 is a zero order reaction. Heterogeneous reaction. Zero order reactions are found in a heterogeneous system. A heterogeneous system, the reactants, products and the catalysts are present in different phases. The well-known examples of heterogeneous reactions with zero order are first, decomposition of hydrogen iodide on the surface of gold, and second, decomposition of ammonia on the surface of metal like platinum, molybdenum or tungsten at high temperatures. In such reactions, the reactant is absorbed on the surface of the catalyst where it is converted into the product. At low concentration, the reaction is first order, but when the surface of the catalyst becomes fully covered with the reactants, the reaction becomes zero order. On increasing the concentration of the reactant, the reaction rates does not change. In other words, the rate becomes independent of concentration and becomes zero order reaction. For example, the decomposition of NH3 on the surface of finely divided platinum is first order when of NH3 in the system is low. However, at high temperature, high pressure, when the surface of the catalyst becomes fully covered with the layer of NH3 molecules, the reaction becomes a zero order reaction. Some enzyme catalyst reactions are also zero order reactions. Integrated rate expressions. We have learned that the instantaneous rate of a reaction is given by differential rate law equations. For example, for a general reaction A into A plus B into B gives us products. The differential rate law equation is dx upon dt is equals to k into A to the power A, k into B into B to the power B. The differential form of rate law is transformed to integrated form of the rate equation. The integrated rate equations for different order reactions can be derived as given below. Zero order reaction. In a zero order reaction, the rate is independent of the concentration of the reactants. Consider a general zero order reaction. Let A be the concentration of reactant and K the rate constant for zero order reaction. Since the rate of reaction is independent of concentration of reactant A, thus rate is equals to K. This is differential rate equation. Rearranging above equation, we get minus d of A is equals to K into dt. Integrating the above equation, we get minus of A is equals to Kt plus I, where I is the constant of integration. The value of I can be calculated from the initial concentration. Let the initial concentration of A be A naught at T is equals to 0. Then above equation becomes I is equals to minus A naught. Substituting the value of I in equation 2, we get K is equals to 1 by T. A naught minus A. This is the integrated rate expression for zero order reactions. The rate constant K can be calculated if we know the concentration of A at any time T and the initial concentration A naught. Ultimately, the rate constant K can be calculated as follows. Let the initial concentration of A be small a moles per liter and let x moles of reactants convert into products in time t. Then concentration of A left after time t be A minus x moles per liter. Rate constant will be out 1x by t. This is a general equation for zero order reaction. It shows that for a zero order reactions, the amount of substances reacted is proportional to the time. Important characteristics of zero order reaction. The integrated rate law equations for zero order reactions are Kt is equals to A naught minus A is equals to minus Kt plus A naught, and K is equals to 1 by T A naught minus A. It can be seen from equation that if we plot a graph between A against T, we get a straight line with slope minus K and intercept equal to A naught. The differential rate law equation for zero order reaction is rate is equals to K A naught is equals to K. It is clear from this equation that rate of zero order reaction is independent of concentration of reactants. Therefore, a plot of rate of reaction versus concentration of reactants will be a straight line parallel to concentration axis. Half-life of a zero-order reaction. Half-life T half of a reaction is the time required for the concentration of reactant to decrease to half of its initial value. T is equals to half, A is equals to A naught by half. Substituting these values in the integrated rate equation, we get T half is equals to A naught by 2K. Thus, the half-life of a zero-order reaction is directly proportional to initial concentration of the reactant. That means in the initial concentration of reactant is made up double, the time required for reaction to be half completed is also doubled, and so on. Units of rate constant K. The rate equation for zero order is K is equals to 1 by time into concentration is equals to moles per. Kinetics of first order reactions. A reaction is said to be of first order if its rate depends upon the concentration variable only. Consider a first order reaction. A gives us products. If the initial concentration of A is a moles per liter and let X moles of reactant get changed into products in time, then the concentration of A after time t is A minus X moles per liter. Then according to law of mass action, the rate of reaction is directly proportional to A. Dx upon dt is directly proportional to A minus X is equals to K minus X, where K is the rate constant or specific rate of reaction for the first order reaction. Equation first is the differential rate equation. Rearranging above equation, we get dx upon A minus X is equals to K into dt. Integrating this equation, we get logarithm of A minus X is equals to Kt plus I, where I is the constant of integration. At the start of reaction, at t is equals to 0, x is equals to 0. Substituting these values in equation 2, we get logarithm of A is equals to 1. Substituting the value of first in equation 2, I in equation 2, we have K is equals to 2.303 upon T log of A upon A minus X. Equation 4 may also be written in an alternate forms as follows. If the initial concentration of A is C naught at T is equals to 0 and time T the concentration of A is Ct, then putting the A is equals to C0 and T A minus X is equals to Ct in equation 4, we get K is equals to 2.303 upon T log of C0 upon Ct. Similarly, equation 3 may then be written as Kt is equals to logarithm of C0 upon Ct. Equation 6 may also be written in exponential form. Taking anti-log of both sides, Ct upon Ce0 is equals to e to the power minus kt. This is very useful form of integrated first order rate equation, as it directly gives the concentration of reacting species at any time if the initial concentration and the rate constant are known. Important characteristics of first order reactions. A first order reaction must obey any of the following rate equations. K is equals to 2.303 upon T log of A upon A minus X. K is equals to 2.303 upon T log of C0 upon Ct. Ct is equals to C naught e to the power minus kt. In a reaction of first order, the rate equation Ct is equals to C0 e to the power minus Kt means that the reaction never proceeds to completion because Ct can become 0 only at infinite time t. First order reaction can be tested by following methods. By substitution method, all the reactions of first order obey the following equations. K is equals to 2.303 upon T log of A upon A minus X. Starting with a known concentration A or C note, the concentration of the reactant or Ct is noted at different intervals of time. The values of concentration or Ct at different intervals are substituted in the above equations. If the value of K comes out to be constant, then the reaction is of first order. By graphical method, equation 5 may be written as plot of log Ct vs T. This equation is comparable to equation of a straight line y is equals to mx plus c. When a graph is plotted between log Ct and time t at various intervals of time, a straight line is obtained showing that the reaction is of first order. This is shown in figure 10. The slope of this line is equal to minus k upon 2.303. From this, rate constant k can be calculated. Alternatively, if we write this equation 8 as log of C2 log of C naught upon Ct is equals to Kt upon 2.303. The plot of log C naught upon Ct vs T will give a straight line with slope K upon 2.303. Calculation of rate constant when initial concentration is not known. Integrated rate equation can be used to test a first order reaction when the initial concentration of a reactant is not known. In such case, the initial concentration term A is eliminated. This is done as follows. Let the concentration of reactant at time t1 is equals to A minus x1, concentration at reactant at time t2 is equals to A minus x2. Then the integrated rate equation can be written as K is equals to 2.303 upon T1 log of A upon A minus x1 and 2.303 upon T2 log of A upon A minus x2. Finally, we will get K is equals to 2.303 upon T2 minus T1 log of A minus x2 upon A minus x1 upon A minus x2. If Ct and Ct2 are the concentrations of reactant at time intervals T1 and T2, then equation can be expressed as K is equals to 2.303 upon T2 minus T1 log of Ct1 upon Ct2. If a plot of log A minus x1 upon A minus x2 or log of Ct1 upon Ct2 vs T2 minus T1 gives a straight line passing through origin with slope K upon 2.303 is obtained when the reaction is of first order. Half-life period of first order reaction. Half-life of a reaction is the time required for the concentration of reactant to reduce the half of its original value. The integrated rate equation is 2.303 upon K log of A upon A minus X. At T is equals to T half of the reactant has released, X is equals to A by 2. Writing half-life time as T half and substituting the value of X in equation, we get T half is equals to 0.693 upon K. The initial concentration term A doesn't appear in this equation, thus half-life of first order reaction is independent of initial concentration of the reactant. Similarly, it can be shown that in a first order reaction, the fractional life periods T1 by 3 and T3 by 2 are also independent of initial concentration of the reactant. For example, time required to complete 1 by 3 of the reaction will be given as, in general, the time required to complete nth fraction of the reaction will be T1 by n is equals to 2.303 upon K log of 1 upon 1 minus 1 by n. Okay, fractional life method can be used to detect whether a given reaction is of first order or not. Units of first order rate constants. The integrated rate equation for first order reaction is K is equals to 2.303 upon T log of A upon A minus X. It is clear that K depends upon the ratio of two concentration terms and time T. The units of K expressed in units of time inverse. Time may be expressed in second, minute or hours. Accordingly, the unit of K are second inverse, minute inverse or hour inverse respectively. Some examples of first order reactions. The first order reaction are broadly divided into two types. First order gas phase reactions, first order reaction taking place in solution. The gas phase reactions of first order are comparatively few. In these reactions, the progresses of the reactions may be followed by measuring the volume of pressure of the gases, reactants or products, whereas for the first order reaction taking place in solution, the concentration of the reactant is measured at different intervals of time. Kinetics of some common first order reactants is taken up in the following discussion. For the sake of simplicity, the examples of first order reactions have been divided into three categories: decomposition reaction of first order reactions involving isomeric change, pseudo unimolecular reactions of first order. Depending upon the quantity that can be measured, the concentration terms in the integrated rate equation may be replaced by quantities like volume, pressure, rotation of polarized light. Decomposition reactions of first order. These reactions involve decomposition reaction in gas phase or in solution. The decomposition reaction which involve the change in number of gaseous molecules. The concentration term in equation K is equals to 2.303 upon T log of A upon A minus X are replaced by pressure or volume terms. Few decomposition reactions of first order are discussed ahead. Decomposition of nitrogen pentoxide N2O5. Nitrogen pentoxide is a volatile solid which decomposes in gaseous form or in its solution in inert solvents like carbon tetrachloride, chloroform, etc. The reaction is represented as N2O5 gives us N2O4 plus half O2, further gives us 2NO3. 2NO2. The kinetics of this reaction may be studied in two ways: by measuring the concentration of N2O5 in solution at different intervals of time, by measuring the volume of oxygen gas produced at different intervals of time. In first case, the following rate equation is used: 2.303 upon T log of A upon A minus Xn. However, the second case, as both N2O4 and NO2 remains soluble in solution while oxygen gas escapes, thus the volume of oxygen gas collected is measured at different intervals of time. The total volume of oxygen collected at the end of reaction gives a measure of the total concentration of N2O5 taken initially. Is the V1 if Vt is the volume collected at any time and V infinity is the total volume collected at the end of reaction, then it is obvious that V infinity is directly proportional to initial concentration of N2O5. Vd is directly proportional to amount of N2O5 decomposed. V infinity is equals to A and Vt is equals to X. Substituting for A and X in above equation, we get K is equals to 2.303 upon T log of V infinity upon V infinity minus Vt. So both forms of rate equation are used depending upon the quantity measured. Decomposition of benzene diazole. Decomposition of ammonium nitrate. Ammonium nitrate in aqueous solution decomposes at room temperature according to following reaction. NH4NO2 gives us 2H2 plus 2N2. The progress of reaction is studied by measuring the volume of nitrogen produced at different intervals of time. The rate equation used is 2.303 upon T log of V infinity upon V infinity minus T. Decomposition of benzene diazonium chloride. Benzene diazonium chloride in its aqueous solution decomposes according to the following reaction. Benzene diazonium chloride converts into chlorobenzene. The progress of the reaction can be studied by measuring the volume of nitrogen gas collected at different intervals of time. The rate equation for this reaction is 2.303 upon T log of V infinity upon V infinity minus T, where V infinity is the volume of N2 collected at the end of reaction and Vt is the volume of N2 at any time t. Decomposition of hydrogen peroxide. The decomposition of hydrogen peroxide takes place according to the equation. The reaction is catalyzed by the presence of finely divided platinum. The progress of the reaction is studied by two methods. By measuring the volume of oxygen evolved at different intervals, the rate constant can be calculated using the equation K. 2.303 upon T log of V infinity upon V infinity minus Vt. By estimating the concentration of H2O2 left at different intervals by titrating H2O2 solution against KMnO4 solution. This can be done by withdrawing small amounts of H2O2 solution at regular intervals and titrating it against a standard KMnO4 solution. The volume of KMnO4 used will be directly proportional to the concentration of H2O2 left behind at any instant. The volume of KMnO4 used before the start of reaction at T is equals to 0 gives the initial concentration of H2O2. Thus, it is obvious that before the start of reaction at T is equals to 0. The volume of KMnO4 used to V naught infinity is directly proportional to initial concentration of H2O2. At time t, the volume of KMnO4 used to be T directly proportional to concentration of H2O2 at time t. So in the first order reaction, K is equals to 2.303 upon T log of A upon A minus X. Substituting these values in first order equation, we will get K is equals to 2.303 upon T log of V naught upon Vt. Thermal decomposition of azeoisopropane. Azeoisopropane decomposes on heating to form hexane and nitrogen according to the equation. It is a homogeneous gaseous reaction because all the reactants and products are in gaseous state. Therefore, the progress of the reaction can be followed by measuring the pressure of reaction mixture at different intervals of time. At the start of the reaction, the initial pressure Pi of reaction mixture is proportional to the initial concentration of azeoisopropane A. For every molecule of azeoisopropane that decomposes, first molecule of N2 and first molecule of hexane are produced. As a result, the pressure of reaction mixture increases with time. At any time, the total pressure Pt is the sum of partial pressure of azeoisopropane Pa, nitrogen Pn2 and hexane Pc6H14 at that instant. At a given instant t, let P be the decrease in pressure of azeoisopropane, then the pressure of each of N2 and C6H14 increases by an amount P. Thus, at any instant, the pressure of azeoisopropane Pa is equals to Pi minus P. The pressure of nitrogen is Pn2 is equals to P. The pressure of hexane is Pc6H14 is equals to P. Substituting these values in equation 2, we get Pt is equals to Pi minus P plus P plus P. P is equals to Pi minus Pt minus Pi. But the decrease in pressure of azeoisopropane is proportional to the amount of azeoisopropane decomposed. Comparing results 4 and 5, we get X is directly proportional to Pt minus Pi. From equation first, we have A is directly proportional to P. Substituting the values of A and A minus X in first order rate equation, K is equals to 2.303 upon T log of Pi upon 2 Pi minus Pt, where Pi is the initial pressure at T is equals to 0 and Pt is the pressure of reaction mixture at time T. First order reaction involving isomeric change. Isomeric conversion of N-chloroacetoanilide into P-chloroacetoanilide is an example of first order reaction. The isomerization takes place in acidic medium as follows. The isomerization reaction occurs when N-chloroacetoanilide is treated with Ki solution in acidic medium. The study of kinetics of this reaction is based upon the fact that one N-chloroacetoanilide reacts with Ki in acidic medium to liberate iodine, whereas P-chloroacetoanilide doesn't liberate iodine. N-chloroacetoanilide reacts as follows. A known volume of reaction mixture is withdrawn at different intervals and the iodine liberated is measured by titration against a standard solution of sodium thiosulfate using starch as indicator. The volume of hypo solution used at T is equals to 0 is proportional to the amount of I2 liberated, which in turn is proportional to the initial concentration of N-chloroacetoanilide. The volume of hypo solution used at time T is proportional to amount of I2 liberated with in turn which depends upon the concentration of N-chloroacetoanilide at that time. Thus, A minus X is directly proportional to Vt. Substituting these values in first order equation 2.303 upon T log of A upon A minus X, the equation takes the form K is equals to 2.303 upon T log of V naught upon Vt. Pseudo first order reactions. These are reactions which are not unimolecular yet they get obey first order equation. Some examples of such reactions are hydrolysis of ethyl acetate, inversion of cane sugar. In these reactions, there are more than one reactant, but the rate of reaction depends on the concentration of only one of the reactants. Consider a general reaction A plus B is equals to products. The molecularity of the reaction is 2, so it is a bimolecular reaction. However, when one of the reactant is present in large excess, then its concentration remains particularly constant during the reaction. Suppose the reactant B is present in excess and its concentration remains practically unchanged. Under such conditions, we may write thus the reaction appears to be of second order but follows first order kinetics. Thus, the reaction which appear to be of higher order but actually follows first order kinetics are called pseudo first order reactions. Consider the hydrolysis of ethyl acetate. The molecularity of the reaction is it 2, so it is by molecular reaction. The concentration of ethyl acetate changes during reactions while water is present in high concentration, and thus its concentration remains particularly constant. Therefore the rate of reaction depends only on the concentration of ethyl acetate, and hence it is a first order reaction. Rate is directly proportional to CS3COOC2H5. Thus, the reaction appears to be of second order but follows the first order kinetics. Thus, the reactions which appears to be of higher orders but actually follows first order kinetics are called pseudo first order reactions. Thank you.